Let's Boltzmann Q&A. What is Strang splitting? So this is again a little bit an advanced question. We have not used the word Strang splitting in the main lecture, but we have used it implicitly, and it is a useful concept. So let us look at the actual problem we are dealing with. We want to solve an approximation of the Boltzmann equation here, and this Boltzmann equation has two main operators, namely the streaming operator and the collision operator, and we want to apply them in the lattice Boltzmann method separately. So we say there is a collision operator C and there is a streaming operator S. And what we do in lattice Boltzmann method, we, for example, first apply the streaming, and then we apply the collision, and then we do the same thing over and over again. And then when we derive from asymptotic analysis or from, say, the Taylor expansion, the equation that we are actually solving, we are only, of course, approximating them. However, we see that we have a significant error term here in this collision operator, apparently, which is the splitting error. So this error here is significant because it will be of first order, so it will actually kill our simulation, because if you do something that is first order, you are considered incompetent. So fortunately, in the very beginning of the lattice Boltzmann method, actually before the lattice Boltzmann method, already in the times of the lattice gas method, it was discovered that this error term can be very easily repaired by just saying that we define a new relaxation time T star as the tau star as the tau minus delta T half. And when we replace this in the Boltzmann equation, we actually have our original viscosity defining parameter here, and everything is repaired and we get to second order accuracy. So, okay, where this is actually coming from is that the splitting is non-commuting. You see, we have to apply the streaming and the collision one after the other, and applying the streaming first and then the collision is different from applying the collision first and then doing the streaming. And because they are not the same, but in the Boltzmann equation they are supposed to happen at the same time, doing them sequentially will lead to an error. And this error will be of first order. So let us briefly remind us how we usually get to operators that are of at least second order, which we want to have. And this is in most cases, for example, by simple finite differences. This is obtained by using centered schemes. Centered schemes are schemes that are somehow symmetric. So suppose we have here an operator big C, which is supposed to approximate this guy here, together with some error term. So suppose this was all a function of delta t, and we have here an infinite sum of error terms, which of course we hope are being small. So when we implement a numerical operator that is symmetric, such that we can actually turn it around so that it's identical to its mirror image, what we see is that in the error terms, all the odd terms have to drop out, and this leads to the condition that when the odd terms are dropped out, all the remaining error terms are even, and therefore we would have at least second order accurate method. However, as I just said, in the Lattice-Boltzmann method, where we have streaming and collision, when we turn the time step around, we also have to turn the order of collision and streaming around, and this is not the same as doing streaming and then collision, or collision and then streaming, and therefore this doesn't work here. So the idea now behind this Strang splitting thing is to make these operations symmetric, and this is an idea that Strang splitting is of course not an idea coming from Lattice-Boltzmann, but the idea to interpret the Lattice-Boltzmann method in Strang splitting comes actually from Paul Dellars. So what he supposed was to look at these operations in a way like this. So we start from distribution F, and then we apply sequentially these operators: collision, streaming, collision, streaming, collision, streaming. And so we come to the end state. So as I said, these things are not symmetric, but the idea was that we can make it symmetric by splitting up one of the two operators, and in principle it does not matter which one we split up. So Dellars decided that we should split up the collision. So what we do half a collision, then we do streaming, then we do half a collision, and this together, so this part here is one operator, and now this operator is symmetric. Yeah, half collision, streaming, and collision. So we can turn it around. It will be doing the same, and of course this has to be connected to another half collision. And Dellars then said that what is this half a collision? Well, half a collision is the average between one collision and doing nothing. So I is indicating the identity here. And by doing this, we would have half collision would be a full collision, which means that doing this splitting is actually exactly the same as doing what we are usually doing in Lattice-Boltzmann: collision, streaming, up to, of course, the start point and the end point, yeah, where we are missing half a collision here. But inside the loop will always do this splitting implicitly. So the good news is, without even knowing it, we were using Strang splitting in Lattice-Boltzmann, and this is the reason why we could get rid of this splitting error just by rescaling the relaxation time. So this was Paul Dellars' proposal, and we are using this splitting too. However, we do it in the lecture in a little bit a different way, and I try to explain why we do it in a different way, because it helps us here with our analysis. As I just said, we can decide which of the two operators, either the collision or the streaming, we split. And Dellars decided to split the collision and leave the streaming the same, where what we are doing is we leave the collision the same and we split up the streaming. So now this means we have to define what is half a streaming. Well, half a streaming is simply streaming half the distance. And this is this can be seen here in our characteristic plot of the Lattice-Boltzmann method, where we plot here the space, and here we plot the time. So what we are doing in one of our symmetric operators. This will be in the middle, it has a collision, and before this it has half a streaming, so streaming half of the distance, and after this, oops, this was the wrong one, after this we have another half streaming. So, and we interpret this by saying that we actually store our collisions in between. So we store not our collisions, our distributions in between the collisions here and here. Okay, and this leads basically to the following equation that is now also useful for the analysis. As we said, the usual lattice-Boltzmann equation would look like this, but you can rewrite the lattice-Boltzmann equation by moving the pre-collision state by 1/2 time step and 1/2 grid spacing, and the post-collision state in the other direction also 1/2, 1/2. And then by recognizing that we will in the analysis, which is now a little bit more complicated and cannot be addressed here in detail, but we will replace the distributions, the pre- and the post-collision distribution, by an average distribution, and we will also have this collision operator. And if you're familiar with the Taylor expansion and you would try and you look at the Taylor expansion of this lattice-Boltzmann equation, you will easily recognize that due to the occurrence of plus and minus here in the opposite directions, you will always observe that half of the terms in F bar will disappear in the Taylor expansion, and half of the terms of the omega will disappear in the Taylor expansion. So this simplifies, so using the idea of Strang splitting in the analysis and shifting the distributions by 1/2 time step and 1/2 grid spacing will drastically simplify our analysis. And also, using Strang splitting is actually not necessary to understand anything that we could not understand already by the Taylor expansion, but it very often simplifies the analysis and the understanding of certain things. For example, the forcing, now this is only an example. If we want to add forcing to the scheme, what we have to do, or what we should do, is we should also implement this in a symmetric fashion, such that our combined operator is still symmetric, and this will automatically imply something that you could ask in another question. So the velocity at a lattice position will usually be the sum over the velocities, the lattice velocities times the distribution functions plus 1/2 of the forcing. This comes directly out of Strang splitting. So you either make a very complicated Taylor expansion to find that this is the case, or you know already that you are using Strang splitting, and then that this is using Strang splitting, and then it becomes very clear that this is the case. So this finishes the question for what is Strang splitting in the lattice-Boltzmann method. Thank you for listening.